I, Sandhya Patidar, on behalf of Applied Mechanics Department, LD College of Engineering, Ahmedabad, welcome you all for the fourth day of 5 days faculty development program on advances on earthquake safe design and construction practice, conducted under AICTE Training and Learning Academy. I hope that you all enjoyed the previous yoga session and will feel fresh and energetic the whole day. Now it's time to start our first session. With due respect, I would like to introduce you all with the revered personality we are having today with us, Dr. Arun Menon, who is Associate Professor of Structural Engineering at IIT Madras. Sir has done his Bachelor's of Architecture from NIT Tiruchipalli and Master's from IIT Madras. Sir holds a first degree in Architecture and PhD in Earthquake Engineering from University of Pavia, Italy. Sir has done varied research in areas like structural safety of historical monuments, seismic behavior assessment, retrofit of existing masonry structures, seismic design of masonry, seismic risk assessment of structures at urban scale, and traditional knowledge system in construction. Sir is author or co-author in these areas in about 75 technical articles. Sir currently coordinates the activity of National Center for Safety of Heritage Structures, a Ministry of HRD supported research center at IIT Madras. Sir was an expert member on the International Coordinating Committee BICC for the UNESCO World Heritage Site of Bagan, Myanmar, and currently is a member in expert advisory group to International Conservation Committee ICC for Wat Phao UNESCO World Heritage in Laos, PDR. Sir has been involved in conservation projects in India, Rashtrapati Bhavan, IIM Ahmedabad, Madurai Meenakshi Temple, in Bhutan, Tango Monastery, in Myanmar, Bagan, and in the Philippines, San Sebastian Basilica, Manilia. Sir has been honored with many awards like Young Faculty Recognition Award in IIT Madras 2016. Best Outgoing Student Regional Engineering College Alumni Association in Tiruchipalli 2000. Architect Kharche Endowment Award for Best Architecture Thesis REC Tiruchipalli 2000. Now, I would like to invite Dr. Arun Menon to enhance our knowledge on the concept of earthquake performance of heritage structures and guidelines. Sir, over to you.
Thank you, Sandhya. Very good morning to everyone who's here at this course. Happy to see colleagues. And my gratitude and thanks to Major Chaitanya Sangvi, who invited me, head of the Department of Applied Mechanics at LDC, who invited me to this interesting program that you are going through this week. As I understand, you had a yoga session this morning for all of you who are at the college. So in continuation, we are in this session probably going to look at our heritage. And that's a nice linkage that I can see with the way the day has begun. I am using the web browser for Teams Microsoft. So I have an issue where when I start sharing the screen, the video gets switched off. So you will excuse me for that. Some technical difficulty, and so I'm not able to use the Teams platform itself.
So, sir, in the MS Team, this is the problem that when we share the screen, it switch off our video.
It's switching off the video. Yes. So I'm sorry about that. I'm just going to start sharing the screen and. Yeah, can you see the screen?
Yes.
Yes, sir.
Yeah, and it is in presentation mode now?
No, it's not in presentation mode. It's in like normal editable mode.
I have made it to presentation mode.
You have to share screen, not the window or something like that.
Entire
Just share the whole screen. Yes, share the entire screen, and then probably it will work.
Okay.
Yes.
Now?
Now, yes, now it is perfect. Perfect.
Okay.
Yes, sir.
Thank you so much. Yeah. So the topic that I've been asked to speak on is earthquake performance of heritage structures and some thoughts on the guidelines for retrofit of such constructions. And this particular course is being conducted, organized by LDCE at Ahmedabad, and most of you, if not all of you, would have had a first-hand experience of what happened about 21 years ago. And there is also a significant effect on monuments and historical and heritage structures in such massive events, which are spread over a very large area. Of course, they're not as frequent, but they still take an important toll on heritage and historical structures. So today, the way I have organized my presentation is to quickly examine earthquakes and built heritage, positioning earthquakes and built heritage together. Unlike regular buildings, unlike modern constructions that we build according to codes, and we have sufficient research and development in many of the modern construction materials and systems, what about historical constructions? The situation is quite different, and therefore we need to have some criteria as engineers for structural interventions, not only as engineers, as architects and archaeologists and conservation specialists who work in the specific field. And therefore, it is important to pay attention to how appropriate seismic demand levels are defined, and to understand if the performance levels and the design demand levels that we prescribe for regular constructions is acceptable for historical constructions. So it's very important to define what is the appropriate seismic demand for historical constructions and what is an acceptable level of performance for such historical constructions. Is it one? Is it multiple? And what is the basis for that? Then it's important for us to be able to estimate system capacity, because we tend to think in terms of a demand to capacity ratio and see if there are inadequacies in the system. And therefore, one has to understand how system capacities for such constructions, which are very often masonry constructions, historical masonry constructions, how do you go about estimating system capacity? And then let's come back to what may be some acceptable structural interventions which are prescribed worldwide. Today, there is a good understanding of what is good for historical constructions, what is not good for historical constructions. And then with those thoughts, we'll conclude this presentation. So, as I said, LD College has been, its position in Ahmedabad, which 2 decades ago saw one of the worst earthquakes in this country. But historical constructions typically have augmented vulnerability to natural disasters. The Bhuj earthquake is just one example. In fact, records previous to the earthquake and post-earthquake tell us that Kutch district alone had about 15,000 enlisted heritage properties, and about 10,000 of them were destroyed or extensively damaged. So you're talking of one event that lasts for a few seconds that can wipe out 2/3 of what human beings have been able to build over centuries. So there's only one event, as I said. There are multiple events: the Indian Ocean tsunami in 2004, the Kashmir earthquake in 2005, the Sikkim earthquake in 2011, the Kedarnath floods in 2013, the Kashmir floods in 2014, Nepal earthquake in 2015, the twin earthquakes, the Myanmar earthquake in 2016. And of course, after that, there have been smaller incidents, but the big ones have given us a respite of about 5 years, 6 years now. And within a context of multi-hazard assessment, it is important that we focus on earthquakes, which are sudden accidental loads that come onto these constructions. But we should remember that these constructions are susceptible to multiple hazards, and that's why floods could be a problem, cyclonic storms could be a problem, and one has to examine it within a context of multiple hazards. One important aspect that we need to keep in mind is the timescales of built heritage and earthquakes. Okay, what's the frequency of earthquakes and how long have these constructions been around? It's important for us to contrast these two to understand that our approach cannot be very similar to the approach to a modern construction, right? And modern constructions have the concept of design life. The structural engineer, the design team chooses the design life of a modern construction. Instead, for built heritage constructions, monumental constructions, you don't have the luxury of choosing the design life. Okay, it's been there for a long time. It's been there even before you and I were born. It was probably here several centuries ago. So one has to immediately contrast the timeline of both earthquakes and built heritage. I'll give you some examples and where the problem really is. The picture that you're seeing here is of a monument in a place called Bagan, B-A-G-A-N, in Myanmar, neighboring country. This photograph is from earthquake damage of one of the monuments. In fact, you'll be surprised to know that Bagan is a place where within a geographical area of 12 square kilometers, more than 3,200 monuments are present even today. It's a World Heritage Site, became a World Heritage Site in 2019. So this is one of the monuments damaged in a big earthquake that happened in 1975. But 2016, and we're talking of 41 years later, an earthquake comparable in magnitude and effect to the same earthquake occurred, and it's the same monument that I'm showing you. Of course, a picture from a slightly different location. There was reconstruction of significant portions of the spire, and in 2016 we see exactly the same damage. So you're seeing a situation of the same monument affected by two significant earthquakes in a matter of 4 decades, within 4 decades. In this context, there's this fantastic book that those of you who are interested in this subject should look at. And the name of this book is conveys everything. In fact, this is one of the few books that I think if you read the title of the book, you understand what the author really wants to say in all the pages of the book. This is a book called Between Two Earthquakes, written by Sir Bernard Fielden, who's considered as the father of modern conservation worldwide. If you go to the website of the Getty Conservation Institute, GCI, Getty Conservation Institute of the Getty Foundation, United States, you will be able to download this book for free. It's called Between Two Earthquakes, Cultural Properties in Seismic Zones. And in the preface to the book, Sir Bernard Fielden very eloquently says, lessons must be learned continually, and we must always be aware that we live between two earthquakes as far as cultural heritage property is concerned, because these have been around for such a very long time. And that's very true. If you're looking at our neighborhood, then you know that the Bhuj earthquake in 2001 was preceded by the Allahabad earthquake in 1819. The Nepal earthquake in 2015 had a history that in 1934 we had the famous Indo-Nepal earthquake. And Bagan, here I was talking about 1975 and 2016. So you see, it may be 180 years, it may be 75 to 80 years, it may be 40 years, and that depends on the seismotectonic setting of the region that we are studying. However, historical constructions are subjected to earthquakes, repeated earthquakes over time, merely because they have been around for such a long period of time. And we as professionals, if you consider each of us, we as professionals will engage with the monument between two earthquakes. So very interestingly, in Bagan, there were engineers, archaeologists, architects who were working on the monument immediately after the 1975 earthquake, and who are today alive and were able to come back and tell us how they worked immediately after the 1975 earthquake, what they had done, and what more should we do to ensure that these structures are protected? Of course, for Nepal and Bhuj, the situation is different, but a professional engineer, an architect, an archaeologist who has an active professional life of 40 years, 50 years, actually has the possibility of not being able to look at two such events, but engaging with the monument between two earthquakes. So you have to learn, you have to pick up lessons from the previous event to ensure that they're not repeated in the next event. Unfortunately, that may not be the case world over. We may be repeating mistakes, and that is where some improvement can definitely be made, because when we lose such heritage, we can never bring it back. It's a loss for history. Now, the same issue of the timelines between built heritage and earthquake in a different context, in a different sense, was also very eloquently put forth, particularly for the Indian subcontinent by Professor Jain, who was at IIT Gandhinagar all these years as director. And I call it the magnitude frequency conundrum of the Indian subcontinent. Professor Jain, in a very interesting paper in 2005, says we have to reflect on the memory and the impact of relatively high frequency of large earthquakes versus relatively low frequency of moderate earthquakes. So if you have a region that is subjected to frequent moderate earthquakes, then the inhabitants of the region in their own lifetime have seen multiple moderate earthquake events and are mentally prepared and change practices, construction practices, to protect their constructions. Whereas if you're living in a region where moderate earthquakes are just too few, don't happen, but the large earthquakes are rather frequent, every 50 years, every 70 years, every 100 years, every 180 years, then the problem is the current generations do not have an idea of what it means to see heavy damage in an earthquake. It may pass 1 or 2 generations before the next massive earthquake comes. Unfortunately, since the memory of the earthquake is not present, the construction practices are not necessarily reflective of the potential vulnerabilities that exist. And this is a problem of the Indian subcontinent, where moderate earthquakes are too few and large earthquakes do occur. The Andamans, the Himalayan region, Bhuj, Kutch Peninsula. So this is a problem peculiar to the Indian subcontinent, and one of the fundamental difficulties we've had in improving earthquake safety in our country. And if you actually look at the 475-year return period global seismic hazard map, you will see that it really reflects the problem that we talk of. Large part of the country is moderate to low seismic zones, and there are regions where large earthquakes can be expected, but the frequency of these large earthquakes versus the frequency of these moderate earthquakes is what is affecting earthquake safe practices in the country. Moving on, this is a picture that sort of captures the spread and the potential risk to built heritage in our country, but only the tip of the iceberg of the built heritage, I would say. This is an updated list. We have today 40 World Heritage Sites, UNESCO World Heritage Sites. Ahmedabad itself can pride itself as India's first World Heritage City. The entire old city is India's first UNESCO World Heritage City. And so if you were to look at the World Heritage Sites, UNESCO protected World Heritage Sites in the country versus the existing seismic zoning map, zones 2, 3, 4, and 5, you can see that almost 60 to 70% of the World Heritage Sites are actually sitting in moderate to high seismic zones, which means these constructions at some point in their lifetime have already faced earthquake effects and will continue to face earthquake effects. Okay, let me now give you a general overview of historical constructions particular to the Indian subcontinent, and take you through the reasons for their vulnerability, the earthquake vulnerability. So one of the most common construction typologies is the post and lintel construction, or the trabeate stone construction. The word trabeate coming from the Latin word trave, meaning a beam. So post and lintel constructions, merely placing lintel beams or beams on posts, is called post and lintel or trabeate construction. And if you were to look at the trabeate constructions, the articulation of the joints between the post and the lintel has been a point of focus. How do you connect the post and the lintel is an important aspect that needs attention. If you look at the post and lintel construction that we're talking of, we are the picture that you see is of very typical constructions in South India. These are called mandapas or mandaps as in North India. You would have single stone pillars, and on these pillars you have beams, capitals, beams, and a heavy roof. And these typically have these typically are controlled by overturning mechanisms, not so much as sliding mechanisms. But if you were to look at different regions in the country where these are constructed, and I take the example of South India or peninsular India, where there is a very large number of such constructions, we don't see any articulation of joint, any specific detail in the articulation of a joint between the post and the lintel. And this possibly is a reflection of a region's low seismicity levels. If you take South India, in the last 500 years, the largest earthquake has been a magnitude 6 earthquake in 1900 in Coimbatore. There is no evidence of any other larger earthquake in southern part of peninsular India. So it could well imply that these constructions are the way they are because this is a low seismic region. However, in these regions, even if there is a moderate event, the consequences can be alarming. So that is something that we need to definitely worry about. If you were to, on the other hand, look at similar constructions in Kathmandu Valley, or even similar constructions in Bhuj or in the Himalayan region in Kangra Valley in Himachal, you will see that the post and lintel constructions go through an important articulation of the joint. You will see tenon and mortise joints, as you can see in this picture here. There's a projection in the stone and a depression in the plinth, or vice versa. You will see that the joints are articulated. You have shear keys that have been introduced in the construction typology, in the construction features. And this is clearly the seismic resistant construction vocabulary, I would say, in these regions. We also see interconnections in stone masonry. So stone masonry is typically built without too much of binding material like a mortar. The mortar is present. The mortar is present more in terms of a leveling agent rather than a binding agent with any tensile capacity. So typical dry stone constructions are connected using dowels in iron and wood. And the classical example that I can think of is the stone constructions in Gujarat. And this is a picture that you see from Ahmedabad itself, Achut Kuki's mosque. The tower had collapsed, partially collapsed in the earthquake in 2001. And examining the construction, we could very clearly see how two blocks of the circular tower were held together with wooden dowels, which are embedded in sockets cut out in the stone and filled with lime mortar. Over time, the wooden dowel would deteriorate, and the lime mortar would get washed away over time, and the wooden dowels then deteriorate, and ultimately you're just left with dry stone construction, which does not have any tensile capacity, nothing that is holding these blocks together. And in an earthquake as severe as the Bhuj earthquake, you could have collapses like the ones that you see here. A similar situation, you can see these are pictures from constructions near Patan in Gujarat. You can see very clearly what I'm talking about. Two stone blocks placed next to each other with a little depression in stone cut out, into which line mortar is placed and the wooden dowel is embedded. And this actually helps to keep these blocks together, something that has zero tension capacity because there is no binding mortar with tensile strength. These dowels help in keeping these dowels, which are in wood, which has some amount of ductility, helps to keep these blocks together. As I said, if you go to Kangra Valley, if you look at Himachal Pradesh constructions in Kangra, this is Kangra Fort, you can see, that Kangra Fort was very badly affected in the 1904 Kangra earthquake. Large parts of the Kangra Fort collapsed in the 1904 earthquake. You can see how the construction actually, possibly the reconstruction, has made use of iron dowels, and these are used to basically interconnect these blocks of stone masonry. Interestingly, as I said, South Indian constructions, these mandapas, you're looking at 16-pillared, tall, symmetric constructions. They could be tall or short, 4-pillared mandapas. You could also have a series of configurations which are even asymmetrical constructions. We have looked at studying these constructions for their earthquake safety because we were interested in understanding the sort of vulnerabilities historical constructions have in low to moderate seismic zones. And interestingly, through limit analysis, rigid block analysis, which is actually quite appropriate for such constructions, which are post and lintel constructions without the use of binding mortar. If limit analysis is conducted, where you identify which is the failure mechanism, the governing failure mechanism, and the governing failure mechanism in this case is really the overturning failure. If you look at this graph here, looking at the available factor of safety for different types of configurations, 4-pillared short, 16-pillared short, 4-pillared tall, and 16-pillared tall constructions. And on the x-axis, you're increasing intensity of earthquake action. And you can see that for the different return periods, probabilities of exceedance, 95 years, 475, 975, and 2475 years, you can actually see that the factor of safety can actually be less than 1 for these constructions. This is the static limit analysis that is conducted, which is typically a lower bound capacity that you would get. Of course, this is in fact, we have just completed on the shake table facility at IIT Madras the first test of a full-scale, mandapa, a 4-pillared mandapa, which tried to understand if what the analytical models, simplified analytical models, tell us is acceptable or not. So with no positive connections, as I said, in South India, in peninsular India, we are really looking at mandapas that are quite vulnerable to overturning. And then once a mechanism is formed, you don't have there is no ductility in these systems. Once a mechanism forms and displacement capacity is exceeded, these systems do not have a capacity any further. So you can have catastrophic failure, sudden catastrophic failure of such constructions. And of course, the roof is heavy, and the roof is roof slab is actually simply seated on the columns that you have, pillars that you have, and there is pre-compression and friction, which is actually keeping providing some amount of resistance. However, in such constructions, sliding failure is not the governing mechanism, but overturning mechanisms. That's simply because the frictional resistance is quite significant. Moving on. If you were to look at the traditional constructions in India, not the historical monumental constructions, but traditional constructions, India has a significant stock of traditional seismic resistant constructions that have developed over several hundreds of years in regions of high seismicity. I'm sure Professor Durgesh Rai and Professor Hemant Kaushik, I don't know if he has spoken to you, but I've definitely spoken to you about some of these interesting constructions. Dhajji Diwari in Kashmir, the Tak construction in Kashmir, the Katkuni construction in the Himachal region, the Ekra or the Assam type construction in Ekra in Assam and Sikkim are important examples. Also another interesting example which is in your neighborhood, which is the poles of Gujarat, and poles in the historical center of Ahmedabad is also another interesting example. While the Dhajji Diwari, Tak, Ekra and Katkuni constructions have a vocabulary of the construction system which is very clearly responsive to earthquake actions, the pole constructions are not that well understood. They have survived well during the earthquakes, but you do not have a very systematic earthquake resistant feature in the poles, and so one needs to understand this quite well. With respect to this, therefore, the question always on my mind has been, were they designed to be earthquake resistant, or are we deeming them to be earthquake resistant, looking at how well they have actually been working, or are those features present in them consciously introduced to ensure earthquake resistance? And there's been enough of examination of this problem by people in Gujarat and elsewhere. And I had this interesting opportunity of studying a little carefully with one of the students from CEPT University, working on conservation, a master's in conservation and rejuvenation. And the reason why one has to look at such problems a little more carefully is a number of these pole constructions, if you take the historical center of Ahmedabad, are undergoing modifications, although they are protected World Heritage city portions of the built heritage. There are simple things like floors that are being added in reinforced concrete or replaced, and a new floor in reinforced concrete is added. New elements in reinforced concrete are added. The question is, how do we understand the original construction? What are the governing characteristics for good response, good earthquake response of such constructions, and what should we be careful about when these are undergoing renovations, these are undergoing expansions or restoration? So, as I said, this is rather well documented, but structural studies on these have not really been done quite extensively. The work actually identified that the shear wall area of the orthogonal walls, the distribution of shear walls in two directions, the connections between these orthogonal walls, the regularity in height, and the state of conservation seem to be the most critical parameters of such constructions. These four factors seem to have a significant effect on the safety of such constructions. So I would call them the most influencing parameters, and any restoration effort, any renovation effort on these constructions have to be very careful in not disturbing these important four parameters. Okay, with that sort of an extensive introduction on the problem of historical constructions in a subcontinent like India, where earthquakes are a significant problem, but we don't have a frequent earthquake problem. The issue of built heritage needs to be looked at very carefully. It's important for us to understand which are the statutory provisions, the doctrines, the documents, the guideline documents available for conservation. In that context, it's important to know that the National Conservation Policy of the Government of India, brought out by the Archaeological Survey of India in 2014, is an important document. It actually is one of the few documents worldwide that says monuments of national importance. And mind you, with the Archaeological Survey of India, there are about 3,690 monuments. Monuments of national importance have to be scientifically assessed and retrofitted where warranted. And it also requires that conservation efforts at any monument have to be accompanied by disaster management plans. So you're looking at 3,690 monuments or sites with so many monuments, which have to undergo a systematic process of assessment and retrofit where required, and disaster management plans also have to be reduced for risk reduction. The two other documents, important documents, these are guideline documents, but the specific rules, specific interventions have not yet been worked out and are in the process of being worked out through specific projects. The National Disaster Management Authority, Government of India, under the Ministry of Home, actually came up with, in 2017, two documents: the Disaster Management Guidelines for Cultural Heritage Sites and Precincts, and the Guidelines for Museums by the same authority. Now, why is the second one, museums, why is it important? Because most often museums are sitting in historical buildings, palaces, forts, and so on. And so the building itself could be vulnerable to natural disasters or even human-made disasters. And the contents are valuable, and one has to be very careful about how contents will behave in an earthquake in a place like a museum. The contents are valuable, they cannot moved around carelessly, they cannot fall. So museums have to be taken care of in a different manner. So these are two important guidelines that you want to make reference to in projects that you're taking up, in specific research work that you want to undertake. It is also the right place for me to talk about what the international practice is, and my reference is to an important scientific committee. It's an international scientific committee that that deliberates on the matter of analysis, conservation, and structural restoration of architectural heritage. The committee is referred to as ISCARSA of ICOMOS. ICOMOS is the International Council on Monuments and Sites. It is an advisory body to the UNESCO on matters of culture. And the ISCARSA is an international scientific committee sitting within ICOMOS, within ICOMOS International. Now, what does ICOMOS state? That you cannot look at cultural heritage purely from an archaeological, architectural point of view, or purely from an engineering point of view as an infrastructure. It is important that you have a combination of scientific and cultural insight when you're looking at such constructions. It's important to identify the different expertise necessary as feeders to the decision-making process as far as historical constructions are concerned. And therefore, you need an interdisciplinary approach. Multiple answers may be right answers, and you have to examine these. In such an interdisciplinary approach, particularly when structural safety is a problem, structural engineering can actually provide the scientific support necessary to ensure safeguard of the building as a whole, ensuring life safety, but also ensuring that the consequences on the identified heritage value are minimum. I'll tell you, give you an example. You take any of the historical constructions in Ahmedabad. There are hundreds of them, and you can take the stepwells, you can take the Sarkej Rosa. There are so many beautiful monuments, and these do get affected in earthquakes. Now, can we go in and say, if you introduce reinforced concrete elements, these are going to be protected? They may be protected, but the consequence on the elements that contribute to the heritage value, those will be lost, or those will be heavily compromised. And that implies that we are approaching the problem from a one-sided perspective, that we want to make it safe. But when you're working with cultural heritage, when you're trying to make it safe, one has to be very careful that you need both scientific approach and cultural insight in arriving at solutions. In this context, I would recommend that you go to the website of ISCARSA and look up documents which give the recommendations for analysis, conservation, and structural restoration of architectural heritage. It's called ISCARSA. Talking of the criteria for interventions in built heritage, my reference is to the draft document which ISCASA is preparing. It's a second document. Earlier there was a guideline document. Now the guideline document is being updated and brings to the table far more interesting concepts of sustainability, of environmental sensitiveness, and so on, when we do activities like restoration and the protection of cultural heritage. So it says the criteria for interventions in built heritage. You have to identify what are the character-defining elements of the built heritage. And mind you, this is not only for the architectural team or the archaeological team. The engineering team also should be able to understand these aspects before coming up with solutions. So understand the character-defining elements of the built heritage. They may be tangible and they may be intangible as well. Meaning, if there is a certain type of carving on the stone, or there's a certain type of painting, or a certain type of sculpture, or a certain type of construction system, that is the tangible, the physical element of the heritage. But the intangible is, it is representing a knowledge that our ancestors had and that developed at a time when science and technology was at a very different stage of development. So there is an intangible heritage which is also present. So one must be able to understand these character-defining elements, and all professionals engaged must understand this. More importantly, one must recognize the limitations of codes. I'm sorry, that's off. Recognize limitations of codes and conventional approaches, because codes and conventional approaches for analysis, for design, have been made keeping in mind modern constructions. These have not been made keeping in mind historical constructions. So these codes, these guidelines may not necessarily address all the issues that historical constructions have. So we must remember that we shouldn't try to force fit codes to historical constructions. There may be other problems in these historical constructions, structural problems, maintenance problems, and we must diagnose these, and diagnosis must be the basis for the therapy. And as much as possible, the therapy should address the root cause of distress. Meaning, I'll take an example. If you go to a doctor with a headache, the doctor shouldn't say, okay, you have a headache, take an aspirin and go home. That may not be the right approach. The doctor should be able to arrive at where the headache is coming from. What is the root cause of that headache? It could be a simple fever, or it could be something more deep-seated like a migraine or something of that sort. So one must be able to arrive at the root cause of the distress and not address in repairing the external signs alone, but try and establish what is going wrong, what may be the root cause, and try to solve that root cause. We must also be able to do a structural performance verification before any intervention. What is the situation? If an intervention is going to be put in place, how do you expect the structure to perform better? And that must be demonstrated to the client before the acceptance of an intervention proposal. We also have to think about the concept of minimal intervention. Now, as a professional called to look at a historical construction, you might want to bring your best expertise. You might want to do everything possible for the historical construction. But for a moment, we have to realize that this historical construction might have been here for 500 years. You and I might have been here for a professional career of 20, 30 years, not more. So we have to be quite humble in what we want to do to the structure and try to minimize that. Be minimally invasive, both in terms of tests that you want to do on the structure, destructive tests that you want to do on the structure, and interventions that you want to carry out. We need to strike a balance between structural safety, protection of the heritage values, and respect for the structure's authenticity. You must ensure that what you're trying to put in place does not disturb the reason why the structure is valuable. Plus, we must also remember that the structure has a character. The structure has its own authentic materials, its own authentic features. We must not try to cover these up or change these inadvertently in trying to make it safe. Now, the issue is when there is a lot of uncertainty in the materials, in the strengths of the materials, in the structural system, when there are uncertainties, we tend to take an overcautious approach. You know that in aeronautical engineering, they try to minimize the uncertainty because you cannot carry so much of weight, because that is, you want to minimize uncertainty so that factors of safety are accurately known and minimized, so that the material consumption is lesser and that the aircraft becomes light. So therefore, you see, higher the uncertainty, higher will be the material required for you to ensure that structure is safe. So that sort of an approach, even in historical constructions, is problematic, because you will end up in introducing so much of new material, so much of new protective system, that it might end up damaging the value of the historical construction itself. We must also try and understand that between strengthening and improving structural behavior, there is a fundamental difference. Strengthening means I can go and I can, jacket a wall with reinforced concrete and strengthen the wall so that it is safe. But is there a way of avoiding something like concrete jacketing? Because concrete jacketing can hide away the original construction and even probably hide away some important features like sculptures or inscriptions or whatever. Is there some other way you can confine minimally, maybe by ties, maybe by some wrapping that can reduce the impact of the strengthening intervention, and you improve the structural behavior in the construction? So the idea is, if you have a material which you take a column, you take a wall under compression, then due to Poisson's effect, there is always a bulging lateral expansion of the material. And if it's possible to introduce some sort of confinement that improves the load carrying capacity, gives additional compression capacity, that's a way of improving the structural behavior of the construction. You give higher factor of safety for compression failure. And so that sort of a approach, that is there a way of improving the structural behavior, not only just going and strengthening the structure, is a very subtle change in the way you want to tackle a historical construction. It's also important, like we said, structural performance verification pre and post intervention is required. It is important to demonstrate that the intervention that you're proposing is indispensable, that it has to be done. You have to be sensitive to cost and environmental effects of the chosen strategy. We live in a world where resources are finite, and we have to be careful that we are not unnecessarily using up material. Sometimes we have to quarry stone, sometimes we have to get burnt clay bricks. So let's be conscious of the cost effects. But let's also be the environmental effects, but let's also be sensitive to cost, because sometimes interventions in historical constructions may turn out to be very expensive, and it's possibly not easy to mobilize that amount of money. Is it essential? Is something that you must again ask. Another criterion is compatibility with original materials and techniques. The original materials are a record of history of how materials were used in the past, processes of manufacture of those materials, skills of artisans, and so on. So we must be careful that the new materials that are being used are compatible with these old materials, not only from aesthetics, but also from mechanical characteristics, strength, stiffness, ductility, thermal properties, and so on. Durability of interventions, we have to ensure that the interventions that we are proposing today last for a few decades and do not, get deteriorated in a few days, in a few years. You carry out reinforced concrete jacketing in a historical construction that's about 500 years old, and in 10-15 years, if the reinforced concrete is going to get corroded, then your intervention is in no way a match to the age of the historical construction. So the durability of the intervention is another important aspect. As I said, try to use minimally invasive techniques and as much as possible non-invasive techniques. So where you don't have to damage the historical fabric to put in place the intervention is a better approach than having to damage the historical fabric to put in place the intervention. We have to think about this concept of reversibility we've been talking about for several decades, that if you put an intervention, you must be able to reverse that intervention. Reversibility of intervention was an important concept. But today we have come to understand that you cannot reverse the state of stresses after you have put in place an intervention. So the concept of reversibility is a farce. You cannot really reverse the situation in the structure. You can at the most remove the intervention. the state of stress might not go back to what it was earlier. So reversibility may not be possible, but removability is something that we must think about in putting in place an intervention. So reinforced concrete jacketing, removability is a question, because if you try to remove the reinforced concrete jacketing, you might damage the historical fabric. But if you put steel ties, unbonded post-tensioning ties around a column, around a wall, then can you remove it? Yes, you can remove it without having bonded it to the historical substrate. So reversibility versus removability is something that we must be able to think about. Repairability and post-natural disaster structural maintainability. The structure will continue to get affected by natural disasters. Lesser maybe because of the interventions, but if there is damage, you should be able to repair that damage. Your intervention should not be such that it is not allowing you to reach the part of the structure which needs repair. So repairability is important. Of course, in the design on paper, you might have very interesting interventions, but these may be physically realizable. That finally it has to be feasible. Someone has to execute this on the site. So one has to think of physically realizable interventions, and you should be able to monitor the structural performance after the intervention is put in place. That you must be able to measure some structural performance parameters. You should be able to see how the structure is responding and so on. So monitorability is another important aspect. Having said that, let me go on to another area, which is something that is being debated today across the world. Some countries have accepted that the appropriate approach is what I'm just about to speak, but in some other countries, it is still a wide open problem, and that is when you're doing assessment, when you're doing seismic assessment of historical constructions, what is the appropriate seismic demand and what is the appropriate performance level? The key concerns, as I mentioned earlier, is if you were to pick up code-prescribed earthquake performance levels, and this is typically defined for modern constructions, new designs and modern constructions, are the code-prescribed earthquake performance levels and therefore the hazard level. You have the design basis earthquake, you have the maximum considered earthquake. Are these appropriate for seismic safety assessment of historical monuments? And in this context, if you were to examine what IS 13935 2009 says, special buildings of monumental nature should be analyzed using seismic actions as per IS 1893 Part 1. But mind you, IS 1893 Part 1 is our seismic design code for new constructions. But 13935 actually tells you should adopt a higher importance factor, say even 2, or adopt the maximum considered earthquake. Right? We know that we use design basis earthquake for seismic design for regular constructions, and we, depending on the importance of the structure, use an importance factor. But you see, 13935 actually prescribes that you use a higher importance factor or a maximum considered earthquake. What does it mean? Your seismic demand is automatically going to be higher. And if you're going to check your historical construction against such a high seismic demand, you will see that the structure is inadequate. And when you see that the structure is inadequate, to make it safe, you will introduce interventions which can compromise the historicity of the historic value of the construction. What about IS 13828? IS 13935 is for retrofit of masonry constructions. IS 13828 is improving the seismic safety of low strength historical constructions. And it says use an importance factor of 1.5 for monumental buildings, irrespective of earthquake zones. So the moment you use a higher importance factor, or the moment you use the maximum considered earthquake, you're simply increasing the seismic demand. Because that's something we want to keep in mind. This will simply lead to substantial retrofitting and strengthening, and that can compromise the historical value of the construction. But there are a few international codes, in fact, a couple of them, which actually suggest a reduced seismic input in comparison to new constructions. These codes say, no, you cannot use the same seismic demand that you're using for a new construction. That's for a new construction. For a historical construction, you might even want to reduce that seismic demand when you're designing the interventions. So what are these documents that I'm referring to? Guidelines for evaluation and mitigation of seismic risk to cultural heritage, prepared by the Ministry for Cultural Heritage and Activities, Government of Italy, talks about identifying what is the reachable seismic safety index for a given historical construction. And it is defined as the ratio between the level of attainable seismic protection compatible with the necessities of the building and the desired level of protection on the category of use and importance. So ratio between the level of attainable seismic protection. You have a structure, how much can you intervene to make it safe, given that the building has important features, important paintings, or has a certain historical value, and what is the desired level of protection that you want to give based on, is it being used as a museum, is it just being used as an archaeological monument, or are people living there, and its importance. And this becomes a reference value for the evaluation of the compatibility of planned use and for the operational decisions on strengthening. So once you are able to check this seismic safety index, then you can even take a decision on whether you will allow people to visit such a building, even if it is, are you going to allow people to go inside? Are you allow people to stay inside? Or how many people will be allowed inside? What type of use you want to put it to? And also on decisions for how much of strengthening you should do in these constructions. And then it's also important to see different levels of seismic evaluation. There are, level 1, level 2, level 3. A level 1 seismic evaluation is qualitative, is just going to look at features, missing features, and identify deficiencies. Then for historical masonry constructions, it is useful to do local collapse mechanisms because there are parts of the structure which may not respond globally with the structure, but undergo local collapse mechanisms, like a parapet, like a gable of a wall of a slope-proof construction, a tower, portion of a tower. So there can be local collapse mechanisms in the construction. So a level 2 will ask you to do check all these local collapse mechanisms. If you remember the rigid overturning of the mandapas, that is actually based on limit principles, which is typically used for these local collapse mechanisms. And then you can do a global evaluation of the construction to see the global capacity of the construction. So what specifically does such a this Italian code say as far as limit states are concerned? Ultimate limit state is for safeguarding against rare and high intensity shaking. A damage limit state is limiting the functionality of the structure, limiting economical and functional damage against a more frequent and a low intensity earthquake shaking. And you might have to actually have another limit state, which is limit state of damage for work of art. You want to limit damage so that paintings are not lost, paintings are not restorable after the earthquake. So different limit states need to be defined. And if you look at the proposed seismic demand against the different limit states, if I'm looking at the ultimate limit state, if I look at the ultimate limit state, SLU is referring to the ultimate limit state based on the category of use, infrequently used, frequently used, and very frequently used, with the in a matrix compared with the probability of exceedance for each category of importance. So there's limited importance, average importance, and elevated importance. So you can see that the probability of exceedance, we're talking of a 10% probability of exceedance in 50 years. Choose the design level. You can see that the prescription is use a reduced value with respect to the regular constructions. So infrequently used with a limited importance with reference to a 10% probability of exceedance in 50 years, it's prescribed that to get to 40% of that value, 25%, 17%, frequently used 25%, 17%, 10%. When you come to 10%, actually coming to the code prescription from regular constructions, modern constructions. So that's one factor is one. very frequently used, limited category of importance, 17% probability of exceedance in 50 years. Average, very frequently used, 10% probability of exceedance. Elevated use, very frequent, elevated importance, but very frequently used, 6.5%. A slight increase in the demand that you're actually prescribing here. But if you see the in the bracket, you can see with respect to the prescription for modern constructions, how much the seismic demand is being reduced from about 50% to about 120%. So in most cases, you're actually seeing the seismic demand being lowered for historical constructions, structures of historical value. For the SLD or the damage limit state also, you can see that it's about 50% to 120%, depending on the frequency of use and the category of importance. So this is one of the codes which prescribes this sort of a framework. Another one is the New Zealand standards. The New Zealand standards for earthquake safety 2017, New Zealand technical guidelines for seismic assessment of existing buildings, parts B and C, A, B, and C, and parts B and C brings in the concept of a percentage compliance to new building standards, and makes an explicit statement that existing buildings need not comply to 100% of the new building standards. So that you will accept a lower safety level as long as collapse prevention is possible. If you can prevent collapse, you have checked for collapse prevention, then you can even reduce the design level of seismic input for designing the interventions at less than 100% the new building standards or percentage of new building standards. Okay. Having said that, so this important aspect of taking a fresh look at what should be the seismic demand and performance levels for historical constructions. You want to save them, you don't want to lose their historicity, you have to strike a balance between the two. You need to estimate system capacity, and therefore modeling and analysis is required. You have to approach it quantitatively and qualitatively, any assessment. So in that context, one important aspect is that we must understand there are fundamental differences for such constructions as far as linear elastic versus non-linear finite element analysis is concerned, particularly because you're dealing with materials which have low tensile capacity, low tensile strength. Their compression capacity versus tension capacity is fundamentally different. In fact, most of these constructions in masonry, stone, or brick have zero tensile strength or almost zero tensile strength. And therefore, the use of linear elastic analysis becomes a problem, and it is better to adopt non-linear finite element analysis. A simple example here, if you take a masonry wall with openings and subject it to a pushover analysis, in-plane pushover analysis, the piers will have, so if you see the outer two piers geometrically are the same, but the decompression level will change because of the overturning moments. The overturning effect of lateral load will change the pre-compression level in the direction of in-plane load that is seen. Pier 1 will have lowest pre-compression, Pier 3 will have highest pre-compression, whereas Pier in the middle might have no change in the pre-compression level compared to the gravity loads that are acting. Therefore, with change in the compressive stress, the shear capacity of these piers will change. So Pier 1 and Pier 3 will have totally different shear capacities because of a changed state of compression. And this linear elastic analysis will not be able to capture. If you do linear elastic analysis and compare it with, because of the differences in the compression capacity and tension capacity of these masonry piers. Linear analysis will give you a totally different picture. You can actually see that the capacity is expected from linear analysis is the same for Pier 1 and Pier 3, whereas in reality, if you do nonlinear static analysis, finite element analysis, you will get a completely different governing situation. So this is extremely important, that it can be captured only by nonlinear analysis, as forces at the ultimate are distributed according to the strength capacity, tension versus compression, and not the elastic stiffness. So linear elastic analysis will tell you elastic stiffness will govern the distribution of demand, but that's really not the case in materials which have different tension and compression capacity. If you have reinforced concrete or steel, the picture is different. You don't have that sort of an issue. So this is an important aspect that one must keep in mind, that it's preferable to use nonlinear analysis. And then you have an entire spectrum of types of analysis, that modeling and analysis that you can do. You can do continuum finite element analysis, where you treat the masonry as a continuum, smeared continuum, and you can then assign tensile capacity, compression capacity, and do the analysis. You can do a lump mass model of structures that can be considered as a lump mass stick model, or you can do a three-dimensional model, depending on which can capture the earthquake, the lateral load response better. Particularly if you're doing continuum finite element analysis, you also want to take a decision on, are you doing a global model, are you doing a local model, a part a structure is being done, can I use a planar model there, can I use a 3D model there? These are small decisions that one will have, important decisions that one will have to take. You can see a full three-dimensional solid model of a monument versus a planar model of a portion of a structure, and these are continuum finite element models that one can adopt. Very often, as I said, you will have dry stone constructions which do not have any binding mortar, and the whole concept of a continuum does not exist. Like brick mortar with brick masonry with mortar can be considered as a continuum, but you might have stone construction, stone on stone construction, where discontinuum is how the construction behaves. So you have to explicitly represent the joints and the units, not as a continuum. And the problem is doing full global models will be challenging because these are very heavy computationally, and so you might want to focus on small parts of the structure for such models. Nonlinear behavior here is in the joints. You give a nonlinear law for the joint, and you model the units, and you have units and interface in this sort of a discontinuum model to study parts of a structure. You can part of a wall or part of a colonnade that you want to study. These are possible. Equivalent frame modeling is something else that is adopted for global analysis, where the masonry building, which is composed of masonry walls with openings, is converted into an equivalent frame modeling with an assembly of pier elements and spandrel elements, the beam column elements, and these are the elements. So this is not finite element modeling where you are providing the stress strain response of the material, but you are actually defining the hysteretic behavior of the element. So I'll take the pier element and give the hysteretic response of the pier element. I'll take the spandrel element and give the hysteretic response of the spandrel element, and assemble the beams and the piers and spandrel elements. I can also choose to have rigid connections between them, which is how typically piers and spandrels are connected. I can give a rigid offset and assemble in 3 dimension an equivalent frame representing the global structure itself. So you can have an idealized force displacement, shear force, shear displacement behavior for the pier, and an idealized force displacement, shear force, shear displacement behavior for the spandrel, and that then becomes the nonlinear inelastic model for the construction. As I said, local mechanism analysis is important for masonry constructions because you can have global behavior. What you can see in the right is the formation of shear cracks in masonry buildings. These are typically in the highly compressed floors of the masonry, whereas in masonry constructions, regions which do not have too much of pre-compression, like the parapet wall, the tympanum, this particular entablature here, or if it is a single-storied structure, the entire facade, these can undergo local collapses. That is not a global mechanism, but only parts of the structure are failing in a rigid manner. And these fail more due to loss of equilibrium than exceedance of the material capacities. The tension crack is formed because of poor tensile strength, but after that, there's loss of equilibrium, displacement demand governs, and these can be checked through local collapse mechanism analysis for seismic verification. So one has to do two levels of analysis using rigid body kinematic analysis. One is at a global level, you have the full global model, whereas at the local level, you can check will parapets collapse, will some gable walls collapse, and so on. So this can be based on limit analysis methods using principle of virtual work to estimate horizontal accelerations required to trigger the mechanism and check if the displacement capacity is available in these small substructures and are they susceptible to failure. So this is something that you can try to estimate. So if you're looking at there's a little example as I'm trying to conclude, a little example where a global analysis is carried out on a historical masonry construction. It was affected. This is in Bagan. This is a protected World Heritage site, one of the buildings, a multi-storied masonry construction. It was affected in the earthquake in 1975 and affected in the earthquake in 2016. After the 1975 earthquake, this structure, which has very beautiful paintings in the interior, underwent retrofitting. But unfortunately, they did retrofitting only in the ground story, not in the upper floor. And in the 2016 earthquake, so in the ground story, they introduced a reinforced concrete band around the structure. And unfortunately, in the 2016 earthquake, damage occurred in the upper floors. The lower floors were protected. The lower floors which had paintings were protected, but the upper floors suffered significant damage in the 2016 earthquake. So we were looking at the structure as a pilot project for further interventions. So the structure was fully documented, and a finite element model was developed from it. A continuum model could be used. We are looking at brick masonry with mortar. And the structural modeling must also be very sensitive to the kind of construction typology. And the reason why I'm showing this is you can see that there's an arch construction, a true arch construction. In reality, this is only ornamental. And behind it, you can see that the arch is actually constructed by a technique called the corbelling technique. So the true arch that you see as a finish is actually misguiding what really happens behind the true arch in terms of the true corbelling technique. So one has to be careful in terms of the construction nuances of the construction and try to see if they really have to be reflected in the numerical models. So you can see the same thing here. You can see one or two layers of true arch construction. They're only like finish because the other construction is a bit jagged. And so this is a good finish for the construction. But the true construction is a corbelling technique. So this needs to be incorporated, at least from a verification point of view, whether it has a role to play in the structural safety. So such checks are essential when you're working with historical constructions, and understanding of these variations in the construction is important. And then we had done the analysis of the structure without any interventions, a structure with the reinforced concrete tie band, which was introduced after the 1975 earthquake, and our model was able to replicate the damage in the 2016 earthquake. After this, we worked out other possibilities, introducing reinforced concrete tie bands in the upper floors, or introducing steel ties, removable steel ties through external post-tensioning on the upper floors, and try to look at the behavior. And we're able to see that the response can be improved by the post-tensioning, external post-tensioning. And we need not really use the reinforced concrete bands for the upper floors. So this sort of a analysis is important. This sort of alternative approaches for seismic retrofit and check performance and see which would be the most appropriate intervention to be carried out. So I think I would be running out of time, and I might stop at this stage because there are few more points. They're more on the interventions that can be carried out. But I'll stop here and just go through one last thought, that it's important to, when you're working with historical masonry constructions, it's important to take a graded approach in the assessment and try to identify what are the weak links in the construction, which you should be able to fix by appropriate interventions and reduce the risk of the construction. So a weak link identification approach proceed for the seismic verification. You start by collecting data, as-built drawings, do a rapid visual survey, document the structure, choose the appropriate level of seismic demand, and then do an initial seismic assessment to check for whether the structure has any vulnerable local mechanisms from the visual inspection, and then check if preliminary code compliances, there mustn't be aspects that are glaring deficiencies in the structure. Check if these are actually satisfied. If they're satisfied, you can go towards more detailed analysis, try to characterize the material properties. And this characterization of material properties, you can either take from existing literature, if you're not able to do it on the structure. Otherwise, if you're able to do it comprehensively on the structure using non-destructive, semi-destructive testing, then you have better information, and you can probably work with lower factors of safety. Uncertainties are lesser. But if you're using data from the literature, then try to use lower bound material properties in the detailed analysis. But when you're doing the initial seismic assessment, if you find that there are vulnerable portions of the structure already, visual examination is showing you, and preliminary code compliance checks are not satisfied, then you have to go, you don't go directly to the detailed seismic assessment. You have to do what we refer to as level 1 seismic strengthening, which is ensure wall-to-wall connections are improved, wall-to-diaphragm connections are improved, ensure that there is a continuous band around openings so that integrity of the wall is maintained. You might have to strengthen the out-of-plane wall, and for this, you will need the seismic demand to be estimated, because you should know how much should be the strength of the connection, what should be the size of the RC, the seismic band. So these constitute what are called level 1 seismic strengthening interventions. Once you do these level 1, once you design these level 1 seismic strengthening interventions, then you want to go and check whether the masonry piers have adequate out-of-plane capacity. You can, and if the demand to capacity ratio is greater than 1, you can go back to level 1 strengthening and do further strengthening like out-of-plane wall strengthening. If the demand to capacity ratios are not greater than 1 for the out-of-plane capacity, then look at the diaphragm, try to characterize the flow diaphragms, because they can play an important part in poor or good seismic response. If the diaphragms are flexible diaphragms, you might want to go back to level 1 strengthening, improve the diaphragm stiffnesses. If they are semi-rigid or rigid diaphragms, you then want to go ahead and determine how different parts of a wall will respond, determine the response of a spandrel. There are interactions that will happen between the spandrel and the pier. So these intricacies in the detailed assessment you can consider between the different parts of the masonry wall for in-plane global capacity. And then you will be able to estimate from the global demand at what level of seismic input or demand is the structure going to reach its capacity, pier capacity or wall capacity, and that you will check whether it is adequate with respect to the seismic demand. And if it is adequate, then you don't need any strengthening improvement of the behavior of the piers. You can stop with level 1 strengthening. If the demand to capacity ratio for the global behavior of the piers is greater than 1, then you will need level 2 strengthening, which may be jacketing the wall, confining the wall. There may be other interventions that you will have to carry out. So this sort of a weak link identification approach is essential to be followed as far as historical masonry constructions, existing masonry constructions are concerned. As I said, I'll stop here and take some questions because it largely covers what I had intended to do.
Thank you so much, sir, for bringing this wonderful session for us. This session was really interesting and helpful. It helps us to broaden our minds on the concept of earthquake performance of heritage structures and guidelines. You made this presentation more useful by using many pictures. You made our concepts more clear by touching topics like criteria for intervention, inbuilt heritage, appropriate seismic demand and performance level, guidelines for evaluation and mitigation of seismic risk to cultural heritage, estimation system capacity, structural modeling for seismic analysis, weak link identification approach, and many more. Thank you so much, sir, for your valuable time. Now, sir, with your permission, can we open for questions?
Yes, please.
Okay, so anyone has question can raise their hands. Is there any questions? Yes.
Yes, Mr. Lokesh, you can ask the
Yes,
question.
Lokesh.
Good afternoon, sir. Am I audible?
Yes, please. Good afternoon.
First of all, I'm sorry, sir. I joined a little late, so I don't know whether my question was answered in the first half. But I would just like to ask my doubt. Sir, whatever additional strengthening elements which you add, is it always necessary to be camouflaged, or is it in some cases left visible also? And at the same time, what are the common camouflaging techniques used so that it doesn't kind of hamper the original look of the building, the heritage building?
Yeah. Thank you.
Thank you.
Let me just show you. Just to answer your question in a more comprehensive manner. So one could, let us say, one wants to introduce some tying of masonry walls. See, masonry connections are important, as I was telling you, and one has to think of level 1 strengthening, which is improving wall-to-wall connections or diaphragm-to-wall connections. So one of the intervention techniques that is typically done in masonry constructions in high seismic zones, moderate seismic zones, is to put steel ties in all the peripheral walls so that the building is tied together, so that local out-of-plane failures are prevented. So if you see this, the two pictures that you see here, close to the floor, you have these steel ties that are running. You'll have to drill through the wall, take this steel tie out, and put an anchor plate on the exterior wall. Actually, if you see this picture, the first picture, you can actually see that another anchor plate of tie coming from a perpendicular wall is attached onto this wall. So basically, on the exterior, you can have these ties running, these anchor plates visible on the surface. or if you want, you can actually hide this away behind plaster. And that completely depends on what the designer's philosophy is, whether the earthquake retrofit strategies, you want the users to be able to see what the retrofit strategies on the building are, or you want to hide it away. And this is completely up to the designer. And if you want it to appear visible to the users, you must be careful about the aesthetics of that. It should not be very different from the original aesthetics of the building, and therefore gives a lot of room for designing it very nicely with respect to the aesthetics of the building. Alternatively, you can hide it away like this. You see that the anchor plate is hidden behind some cut open in the masonry and embedded with the mortar and grout. This is a classical example to tell you what can be done. Either hide it away or make it part of the aesthetics. The usefulness of making it part of the aesthetics is you can communicate to the users that a certain seismic strengthening or seismic improvement intervention has been carried out. It increases the awareness of safety among the end users.
Thank you, sir.
Thank you.
Is there any more questions? Okay. Thank you, sir, for answering all the questions. Sir,
Thank
it would
you.
be great if you can share your PPT with us. It will be benefit for all of us.
Yes,
Thank
I'll
you,
send
sir.
it. Yes.
Thank you so much, sir.
Thank
Now
you.
there will be break till 12 and next session will be of Dr. Sharad Kumar Purohit on earthquake performance of masonry structures and retrofit strategies at sharp 12. So be ready for the next session.
Thank you. Thank you, Major Sangvi as well.
Thank you very much, sir.